Hi, and welcome to this series designed to cover the Edexcel Year 1 Mechanics syllabus. This video is designed to give a short introduction into modelling and mechanics. But before we jump into some examples, let's try and understand what mathematical modelling is all about. So the aim of mathematical modelling is to solve real-world problems. This could be anything from the forces exerted when two vehicles collide, or the speed at which a diver enters the water. Whatever the scenario, to make our lives easier, we will need to always make some sort of assumptions. Let's take the case of our diver. We could assume that his or her mass is concentrated at a single point instead of unevenly spread throughout their body. Additionally, we may also want to neglect things such as air resistance. Making these assumptions will allow us to simplify and ultimately solve our problem. But at this point we have to take a step back and ask ourselves, is the answer reasonable? Whether an answer is reasonable or not depends entirely on what you're designing the model for. If you're modeling a safety critical part on an aeroplane, you will probably need a very accurate answer and will therefore make very few assumptions. On the other hand, in the case, say, of our diver, we may just want a ballpark figure, so we may make more assumptions. In reality, all models have to strike a balance between being accurate and computationally efficient. And by computationally efficient, I really just mean how quickly they can be solved on a computer. To get this balance right requires taking lots of iterations and is nearly always a work in progress. But eventually, after several iterations, you get there, and that would be your final solution. Now let's take a look at some examples. Question 1. The motion of a golf ball has been modelled by the equation you can see, where h is the height of the golf ball above the ground in meters, and x is the horizontal distance the golf ball has travelled, also in meters. We want to find the height of the golf ball when it is initially struck. In part B, we want to find the height of the golf ball when it has travelled a horizontal distance of 60 meters, and in part C, we want to find the height of the golf ball when x equals 72, so the horizontal distance travelled equals 72, and we want to comment on this answer. Let's start by drawing a quick diagram so we can visualize what's going on. We have our golf ball that's been modelled using a negative quadratic equation, so we'll probably follow a path something like this. We know that x represents the horizontal distance travelled, and h is the height of the golf ball above the ground. So in part A, we're trying to find the height of the golf ball when it is struck. Well, what would x be when the ball is struck? It would be 0, as the golf ball has not covered any distance horizontally. So we can simply sub x equals 0 into our equation, and we get our answer that h equals 0. This makes sense, since at the moment the ball is struck, it will be on the ground. In part B, we want to find the height of the golf ball when it is at a horizontal distance of 60 meters. This is very similar to part A, but instead of setting x equals to 0, we set x equal to 60. So h equals minus 0.01 multiplied by 60 squared plus 0.7 multiplied by 60. This works out at h equals 6 meters. In the final part of our question, we have to work out the height of the golf ball when x equals 72 meters. This follows exactly the same process as parts A and B. But when we work out the solution, our answer comes to minus 1.44 meters. This doesn't make any sense, since the golf ball cannot travel below the ground. So we can simply comment that the model is not valid when x equals 72, as the golf ball would be below ground level. Now let's have a look at a slightly harder example. John throws a baseball and the motion of the throw can be modelled by the equation shown. Same as in question 1, h is representing the height of the ball above the ground, and x is the horizontal distance travelled. We want to find the range of values for x for which the model is valid, and the model is considered valid when h is positive, so this is when the ball is above the ground. In part B, we want to find the two values for x for which the ball is 5.2 meters above the ground. As before, let's start with a diagram. The diagram is almost identical to the one we had in question 1, but note that the trajectory of the ball does not start from the ground, but from some height above the ground. This is because if we sub x equals 0 into our equation, then h, the height of the ball, comes out to be 1.2 meters. So the ball is thrown from a height of 1.2 meters above the ground. Okay, so in part A, we want to find the range of values for x for which the model is valid. So where is the tipping point between the model being valid or invalid? It is when h equals 0. When h is positive, the ball is above the ground, so we're all good. But when h is negative, the ball is below the ground, which doesn't make any sense. So let's set h equal to 0, and therefore find what the value of x is when we get to the point when the ball hits the ground. So subbing h equals 0 into our equation gives us 1.2 plus 1.5x minus 0.04x squared equals 0. How can we solve this to get x? We have to use the quadratic formula. Just a quick reminder, when we have a quadratic equation in the form of ax squared plus bx plus c equal to 0, we can find the value of x using the quadratic formula. So that's x equals minus b plus minus the square root of b squared minus 4ac, all divided by 2a. So let's rearrange our equation a bit to get it looking closer to the ax squared plus bx plus c equals 0 format. We can now see that a equals minus 0.04, b equals 1.5, and c equals 1.2. Always be careful with the plus minus signs when using this formula. We can sub the values for a, b, and c into our quadratic formula, and we get our two solutions for x as either minus 0.8 meters or 38.3 meters. Now minus 0.8 meters makes no sense in our scenario, as this means that the ball has somehow ended up behind us, which is not feasible. But 38.3 meters does look good. So what is our range for which the model is valid? Well, that is from the moment the ball is thrown to the point at which it lands back on the ground at a horizontal distance of 38.3 meters. And what is the value of x when the ball is thrown? Well, x would be 0. So to answer the question, our model is valid when x is greater than or equal to 0 and less than or equal to 38.3 meters. In part B, we have to find the two values for x for which the ball is 5.2 meters above the ground. So this is actually a very similar process to part A, but instead of setting h equal to 0, we set h equal to 5.2 meters. So we get 1.2 plus 1.5x minus 0.04x squared equals 5.2. Let's minus 5.2 from both sides and then rearrange into the format ax squared plus bx plus c equals 0. We can now see that a equals minus 0.04, b equals 1.5, and c equals minus 4. So we can sub the values for a, b, and c into our quadratic formula, and we get our two solutions for x as either 2.9 meters or 34.6 meters. So the ball crosses the 5.2 meter mark at a horizontal distance of 2.9 meters and this is as it's travelling up, and then at a horizontal distance of 34.6 meters as it's coming back down to the ground. Let's look at one more question. A football is kicked from the edge of a cliff into the water below. The height of the football above the water level, h meters, after t seconds can be modelled using the equation h equals 80 minus 6t squared plus b, where a and b are both constants. We get given the information that the cliff is 15 meters above the water level, and the ball enters the water 3 seconds after being kicked. We have to find the time, t, when the ball is 6.4 meters above the surface of the water. As usual, let's start by drawing a quick diagram. We have our football kicked from the edge of a 15-meter high cliff, where h is the height of the football above the water. So first thing, let's try and work out what our constants a and b are. Once we have a and b, to get our answer, we just need to use the same method as in question 2. We know that when t equals 0 seconds, the ball is at the top of the cliff, so h, the height of the ball above the surface of the water, equals 15 meters. We can sub this information into our equation, giving a times 0 minus 6 times 0 squared plus b equals 15. So of course this leaves us with b equals 15. Now we just need to find a. We know that the ball hits the water when t equals 3 seconds. So when t equals 3, h equals 0. Subbing this into our equation gives a times 3 minus 6 times 3 squared plus b. But of course we now know that b equals 15, and this all equals 0. So we can simplify and solve this, where 3a minus 54 plus 15 equals 0. Therefore we get that 3a equals 39, and a equals 13. Now that we know a and b, we've got our complete equation, that h equals 13t minus 6t squared plus 15. Our question asks us to find the time when the ball is 6.4 meters above the surface of the water. So that's when h equals 6.4. We can sub this into our newly found equation, giving us 13t minus 6t squared plus 15 equals 6.4. Let's minus 6.4 from both sides, giving us our equation in the usual form, ax squared plus bx plus c equals 0, where a equals minus 6, b equals 13, and c equals 8.6. But of course in this case, instead of solving for x, we're solving for t, the time in seconds. As usual, we use our quadratic formula, minus b plus minus the square root of b squared minus 4ac over 2a, and we get our two solutions for t. T equals minus 0.5 seconds, and t equals 2.7 seconds. Of course, we can't have a negative time, so our answer must be 2.7 seconds.